Okay, in this lecture, which is going to be from chapter 6, we're going to do proof by contradiction. Okay? Let me remind you of what we did in the last lecture, which is proof by contraposition. Okay, let me remind you of how that was. So we had a proposition which was something like this: P implies Q. Okay, and you do the proof by supposing the negation of Q and deriving the negation of P. Okay, now what we're going to do this time is going to be proof by contradiction. Which is where you have a proposition and I'm just going to put P. It could be anything, not necessarily a conditional. Okay? And what you do is you suppose the opposite of what you're trying to prove. And then you derive a contradiction of any kind. Okay? Now, these two things are very closely related. In fact, a proof by contraposition is actually a special type of proof by contradiction. Because what you're doing in a proof by contraposition, it depends on how you word it, but you can word it this way. If you had a proposition which was P implies Q. Okay, if you started off by saying, suppose P does not imply Q, then what does that mean? That means you have P and not Q, right? And then if you used this part right here and you derived not P, then you would have P and not P, which is a contradiction, isn't it? So every proof by contraposition can be worded this way, and if you word it that way, then you see that it is a proof by contradiction. So what I'm trying to say is every proof by contraposition is in fact a proof by contradiction. Okay? And the reason why I'm pointing that out for you is because there's an awful lot of people who don't even use the term proof by contraposition. They will just use the term proof by contradiction for both of these types. Okay? So if you mention to somebody, oh, let's do a proof by contraposition, and they say, what does that mean? I've never heard that before. Then that means that they've been taught to just use the name proof by contradiction for also proof by contraposition. Okay? But our book spells them out in different sections, and I think that's a good idea, to be honest with you. So I'm glad that we did proof by contraposition first as a separate category.
I have a question.
Okay, and now we're just going to do these all other proof by contradictions. So you have a proposition. You start by assuming the negation of the proposition, and you derive a contradiction. That then means that the negation is not true. And if the negation is not true, then the original proposition had to be true. Okay, so let's practice this. We're going to do some very famous proofs. So we're going to start by proving that the square root of 2 is irrational. This was originally done by Archimedes, and this is the way that he did it. Okay, so here's what we're going to do. We're going to start by supposing the negation. So what's the negation of being irrational? Is being rational. So we are going to suppose the square root of 2 is rational. Okay. If we call this statement P, then this statement is the negation of P. Okay? All right. I want to try to derive a contradiction of some sort. So, where am I going to go from here? Well, if the square root of 2 is rational, then what does that mean? It means it can be written as a ratio of integers, and that ratio of integers can be written in reduced form. So I say suppose 2 is a rational number. Then the square root of 2, I think I said 2 a second ago, I mean the square root of 2, of course. The square root of 2 equals a over b, where a and b are integers, and this fraction a over b is reduced. What's the easiest way of saying that? The greatest common divisor of a and b equals 1. Okay? Every rational number can be written as a reduced fraction of integers. Okay? All right. Thus, 2 would equal a squared over b squared. What did I do there? I just squared both sides, so it's just algebra. Hence, a squared would equal 2b squared. So what's that tell us about a squared? That tells us that a squared is an even number because it's 2 times an integer. So I write, so a squared is even by definition of even. Okay? Now, since a squared is even, that means that a is even. Right? If a squared is even, then a has to be even. Because a squared is divisible by 2, and 2 is a prime number. So that means a would have to be divisible by 2. Okay? All right, now, if a is even, that means that a equals 2 times an integer. Okay? So, a squared would have to equal what? 4 times that integer squared. You agree with that? Okay, now, up here we have a squared equals 2b squared. And here we have a squared equals 4k squared. So what does that mean? That means that 2, hold on a second, my computer's freaking out. 2b squared must equal 4k squared. So b squared would equal 2k squared. So b squared is even, by definition of even. Then b is even, because if b squared is even, then b is even. So look here, we have a is even, and b is even. So what does that mean? That means that the number 2 is a common divisor of a and b. So the greatest common divisor is at least 2, right? The greatest common divisor of a and b is at least 2, because a and b are both even. But that contradicts the greatest common divisor of a and b equals 1. There's our contradiction. These two things cannot both be true. So I write it like this. This contradicts the fact that the greatest common divisor of a and b is 1. Therefore, so let's point to this out now. Okay, let me shrink this down so we can see the whole thing. Okay, get rid of this extra stuff here. So we started with this supposition. That supposition leads to a contradiction. which means that our original supposition cannot possibly be true, which means that its negation is true. And that's what we were trying to prove in the first place. So we are done. Okay, let's go through this again one more time. We're trying to prove this. Let's just call it P. We assume the negation of P, and we show that the negation of P causes a contradiction, which means the negation of P cannot be true. So therefore, the negation of P has to be true. But what's the negation of the negation of P? It's just P. See how that works? That is a classic example of a proof by contradiction. Archimedes came up with this proof several hundred years BC. Okay, here's another example from Leonhard Euler. The proposition is there are infinitely many primes. Okay, so let's prove this by contradiction. So you start by supposing the negation. So I will start with suppose there are finitely many primes. Okay. Well, if there's finitely many, then we could list them. So then we can list all primes as prime 1, comma, prime 2, comma, and so on and so on. The point being that if there's only infinitely many, then eventually I would get to the end of the list, and we'll call the last one Pn. Okay? If you want to, you could say that list is in order, so that P1 is the number 2, P2 is the number 3, and so on. But that actually doesn't matter one way or the other anyway, so I'm not going to bother even putting that on. Okay? Now, let A be the product of all of those, P1 times P2, all the way up to Pn, okay, plus 1. Now, that number A has to be divisible by a prime number. Okay? Since A is an integer and A is greater than 1, how do I know it's greater than 1? Because it's 1 plus the product of all of the primes. Okay, so since a is an integer that is greater than 1, then a is divisible by some prime number. Let's call that P sub k. P sub k has to be somewhere in this list because that's the list of all the prime numbers, right? So P sub k has to be somewhere in that list. Okay, so because a is divisible by P sub k, that means that a equals P sub k times some integer, let's just call it b. Okay? So hence, we have this. B times P sub k, whoops, I don't know why I put an equal sign. Okay, B times P sub k equals, it equals A, right? Look at this. B times P sub k equals A, but also A equals the product of all the primes plus 1. So let's write B times P sub k equals the product of all of the primes plus 1. And let me also point something else out. P sub k is one of those prime numbers. So P sub k is somewhere in this list. Where is it? I don't know, but I can definitely tell you this. It's somewhere in that list. So here's how I'm going to write this. I'm going to write P1 times P2, so on, so on, so on. Somewhere in that list is pk. Which prime number would come right before pk would be pk minus 1. Which prime number would come right after pk would be pk plus 1. And then the list continues until it gets to the end, pn. Okay, so here's A, and here's A. So those two things must equal each other. Okay? Now, divide both sides by pk. If we divide the left by pk, we get b. If we divide the right by pk, then first of all, that will cancel. And we will have p1 times p2, so on, pk minus 1, and then the next one would be pk plus 1, and then so on, and then up to pn. Okay, and then we'll have plus what? Well, we divided both sides by pk, right? So we'll have plus, stop it, 1 over pk. Do you follow my algebra there? I just took this equation and divided both sides by pk. If it makes it easier for you to follow, then you can put parentheses around this. If that makes it easier for you to follow. Okay? And last step is to subtract this part from both sides. And we get b minus all of that stuff equals 1 over pk. And believe it or not, there's our contradiction. Because the left-hand side is what kind of number? It's an integer. An integer minus a product of integers is an integer. But the right-hand side is not an integer, because pk is a prime number, which means it's bigger than 1, so 1 over pk cannot possibly be an integer. And that's our contradiction. Okay? So, we wanted to prove p. We supposed its negation. We derived a contradiction. So therefore, our supposition could not possibly be true. So its negation must be true. And what's the negation of p is p. Okay, so let me just finish the proof. Therefore, it is not the case that there are finitely many primes. Or in other words, there are infinitely many primes. Okay. Some people even like to put in that line that I said. Let me bump that down. Some people even like to say, therefore, it is not the case that there are finitely many primes. Okay, and this proof comes from Leonhard Euler in around sometime in the Middle Ages. I don't remember exactly when he lived. I want to say it was the 1700s, but I might be off by 100 years. All right, let's do one more example. This one's not a famous one, but it's still good practice. Let's prove for every x from 0 to pi over 2, comma, sine of x plus cosine of x is at least 1. Okay, let's do a proof of that by contradiction. So we suppose the negation. What would be the negation of that statement? The negation would be there is some x from 0 to pi over 2 such that sine of x plus cosine of x is less than 1. Okay? That is the negation of what we want to prove. Okay? Well, what do you know about sine of x between 0 and pi over 2? And also, what do you know the same thing about cosine of x between 0 and pi over 2? We know that they are both non-negative, right? We know that for all x between 0 and pi over 2, sine of x and cosine of x are both equal to or greater than 0. Okay? Let's write that down. So sine of x is equal to or greater than 0, and cosine of x is equal to or greater than 0, since x is somewhere from 0 to pi over 2. Okay? Hence, sine of x plus cosine of x is equal to or greater than 0 and less than 1. I want to point out to you that x is not actually a variable here anymore, because x was set right here. It says there exists some x. So x is a specific value. I don't know what value it is, so I used a variable to name it. But that variable is playing the role of a specific number. Okay? That's very important to understand. All right. Let's take that last line where we just left off, and let's square the whole thing. And we would get 0, because 0 squared is 0, is less than or equal to sine of x plus cosine of x squared, which would be less than 1 squared, which is 1. Okay? Now, what is that in the middle? Isn't that sine squared plus 2 sine x cosine x plus cosine squared? Let's write it that way. In other words, 0 is less than or equal to sine squared x plus 2 sine x cosine x plus cosine squared x, and this is all less than 1. But isn't that middle part there equal to 2 sine x cosine x plus 1? Because don't these two added together give us 1? Okay, so I'm going to write but sine squared x plus 2 sine x cosine x plus cosine squared x equals 2 sine x cosine x plus 1. Thus, two sine x cosine x plus 1 is less than 1. Where am I getting that from? Just right here. Okay. I had that. And then I pointed out that that stuff in the middle there equals 2 sine x cosine x plus 1. And then I just put that right here. Okay. I could have also put the 0 there, but I don't need to, so I just left it off, that's all. Okay, hence, let's take the previous line there. Let's just subtract 1 from both sides. 2 sine x cosine x is less than 0. Which means it's a negative number, right? You could even divide both sides of that by 2. Sine x cosine x is less than 0. But that's a contradiction because look at what I have already said up here. Sorry. Sine x is non-negative and cosine x is non-negative, so how can their product be negative? That's impossible. So I'm going to write this contradicts the fact that sine of x is equal to or greater than 0 and cosine of x is equal to or greater than 0. Therefore, our supposition must have been wrong because it leads to our contradiction. Here was our original supposition, and it leads to a contradiction, so it must be false. So therefore, sine of x plus cosine of x must actually be equal to or greater than 1 for all x from 0 to pi over 2. Okay? And then there's something else I want to say about that, but go ahead and just look so far. Okay, now there's part of this that is a common place to cause confusion. There's nothing that's wrong here. I'm not saying we should change something because it's wrong, but I am saying there is a common place for confusion, and we can avoid the confusion by making a minor change. The confusion goes down to, back what I said earlier. right here, the value of x has been set. I don't know what it is, but it is something specific. It says, suppose there is some specific value between 0 and pi over 2, such that. Okay? So that x, in all of these steps here, that x is playing the role of a specific number, not a variable. Okay? But then here at the last line, x is playing the role of a variable again. Why? Because when we got here, we figured out that this is wrong. So there's nothing wrong with what we did. Everything is valid. But nonetheless, having that x sometimes being a specific value, sometimes being a variable, can confuse people. So here's what a lot of people do, and I think it's a really good idea, is don't use x for a specific value. Instead, what a lot of people do, and I think it's a good idea, is to call that specific value x naught, which is x with a subscript of 0. Because that's very easy to do. You don't have to go out of your way. It's just putting a little 0 there. It's not a lot of extra work. And then you never have to worry about, is x a variable or a specific value? Because we have, in all of here, x is a variable and x naught is a specific value. So I highly encourage you to do this. When you are going to be talking about a specific value, but you don't know what that value is, then go ahead and use a variable name for it and put a subscript of 0 on that variable. So now there's no confusion. X is a variable, x naught is a specific number. Okay? And then when we get to the end, we say, therefore, it is not the case that there is some x naught from 0 to pi over 2, such that sine of x naught plus cosine of x naught is less than 1. That's what we're saying in this last line. Okay, that line right there is literally saying, therefore, it is not the case that there exists some x naught from 0 to pi over 2 such that sine of x naught plus cosine of x naught is less than 1. So it is not the case that there exists such an x naught. How do I say there is not the case that there exists such an x naught? Well, the negation of an existential statement is a universal statement. That's why the phrase for all x between 0 and pi over 2 shows up. Okay? All right, we're going to do more examples of this in the next lecture. These 3 examples came out of the book in section 6.1, and section 6.2 is really just more examples of proof by contradiction. So we'll do that in those examples in the next lecture.